Hello everyone from Math 2000, Linear Algebra. It's Professor Wenson here again with a video on your ZyBooks Section 5.1 titled Vector Spaces and Subspaces. Alright, so now we're going to get into some more abstract material. Chapter 5 of your book is titled Euclidean Vector Spaces. And then in Chapter 6, we're going to get into a chapter titled General Vector Spaces. All right, so a vector space is a very special kind of set. It's a set of objects called vectors, along with a set of scalars, which are usually going to be the real numbers. Scalars, you've seen scalars before. So you have a set of objects, the vectors, a set of scalars, and then two operations defined on that set. One called vector addition, which you've seen an example of, vector addition before, and the other called scalar multiplication, which again you've seen examples of with vectors before in the previous chapter. And these operations, vector addition and scalar multiplication, need to satisfy 10 specific properties in order for that set of objects to be considered a vector space. Right. And then a subspace is just a subset. Right. It's a subset of objects from a vector space that itself is a vector space. So like you might consider a subspace, a smaller vector space, right? A subset of a vector space that satisfies all the same properties. So let's get into this. Right? There are a lot of these properties you're going to need to know. All right. So this one I'm going to read. Right? This is important. Right? A vector space is a very important concept. You are going to hear the words vector space a lot for the rest of the course. All right, chapters 5 through 9. You're going to hear the word vector space and subspace a lot. All right, so the set of all possible vectors with a given number of components is called a vector space. The vector space of all vectors with 3 components can be interpreted as the set of all possible directed line segments in R3. Right, you've seen this notation before. Right, R3 meant the vectors with 3 components that were all real numbers. Okay, so like 1, 2, 3, 3, pi, square root of 2, that kind of stuff. All right. Different vector spaces are formed by vectors of different components. All right, so R2 is a different vector space than R3. R3 is a different vector space than R4, and so on. Right? If you have a different number of components in your vectors, the set of all vectors with that many components is a different vector space. So that is, the set of all vectors with 2 components is a different vector space from the set of all vectors with 5 components, right? Their example there. However, all vector spaces share certain properties, right? This is key, right? Certain properties need to be true, need to hold in order for a set of vectors to be considered a vector space. Also, certain subsets of vectors, right? So like smaller sets, called subspaces, have the same properties as vector spaces. Right, so all the same properties hold, but for a subset of those objects. Right. So the objectives here, the breakdown of the sections. In one part of this, you're going to determine when two vectors are equal, and this is the easy part. Two vectors are equal if all the corresponding components are equal. We're going to look at all the properties of vector spaces. What are these properties they speak of that need to hold in order for a set of vectors to be considered a vector space? And then they mentioned subsets of vectors that have the same properties. These subspaces, well, we're going to also look at a subset of vectors and determine whether or not that subset of vectors is also a vector space, right, or a subspace. All right, so first, the vector space is called Rn, right, like r to the nth here. Now this is vectors with n components where each component is a real number. Right, so the notation R3, as you've seen, represents the set of all ordered triples, right, vectors with three components, x1, x2, x3, where x1 and x2 and x3 are real numbers. Rn is called the n-dimensional Euclidean space, right? So R3 here is three-dimensional Euclidean space, right? Named after ancient mathematician Euclid, a Greek mathematician. R4 is four-dimensional Euclidean space. R2 is two-dimensional Euclidean space. And it consists of all possible n-tuples. Again, vectors. Well, we're going to write these as vectors in a second, or at the brackets. Vectors with n components, and each component is a real number. All right. Since the terminal point uniquely identifies a vector in standard position, the set of all n tuples Rn can also be seen as a vector space. Right? A n-dimensional Euclidean vector space is the set of all vectors with n components, and each component is a real number. So pretty much the same thing. For which scalar, all right, now here's what I mentioned earlier. So you have a set of vectors. You have a set of vectors where all these n component vectors with real number components. Euclidean vector space. So you have a set of vectors. You have scalars. Now the scalars are going to be typically real numbers. Right? And with those vectors and scalars, you have two operations. Scalar multiplication is one of those, and vector addition is the other one. Right? These two operations need to be defined in some way such that certain properties hold, and we'll get to those properties in a little bit. But it's a set of all vectors for which scalar multiplication and vector addition are defined. Okay. Vectors in Rn can be expressed as rows or as columns. So you see a column with n components, a column matrix, or you see a row vector or like a row matrix with the same components. They represent the same thing, the same vector. Now I mentioned this already. Two vectors, u with n components and v with n components, are equal if the corresponding components are equal for all components. Right? So notice they have to have the same number of components in order to possibly be equal. All right, so pretty easy example to start with. So I'll show you these two real quick. All right. So here's the first of those in this example. Now both of these are vectors in R4. Right? You got four components, and each one's represented by a real number. Right? We're supposed to assume these are real numbers here. Now, these two vectors are only going to be equal, again, if the corresponding components are equal. So these are only going to be equal if x plus 2, right, the first component on the left, is equal to 1. Or in other words, if x is negative 1, right, subtracting 2 from both sides. 4 is equal to 4. The second components are already equal. They're only going to be equal if the third components are equal as well, right? So, and on top of this, y minus 3, the third component on the left, needs to be equal to 7, right? The third component on the right. Or in other words, the value of y needs to be 10. And lastly, the fourth components, right? Only if 0 is equal to z, right? So if z is 0, y is 10, and x is negative 1, then both of these will be the vector 1, 4, 7, 0. Right? If I replace x, y, and z with these values, these vectors will both be the vector from R4, 1, 4, with components 1, 4, 7, and 0. Right. Now the other one looks like this, the other example. So the other example is this statement. So I've got this vector on the left here. Notice it has 5 components, right? A, 2, 5, B, and 2. So this is a vector belonging to, right? You've seen hopefully this symbol before. It's a little epsilon, means belongs to R5. This is a vector from R5, right? A vector with 5 components that are real numbers. Now this other side, over here, this is a vector belonging to R3. All right, it's a vector with 3 components. These do not have the same number of components, so they cannot possibly be equal. So this cannot happen. Right? It's impossible to find values of A and B that would make this a true statement. Right? So this cannot happen. The number of components aren't the same. Alright, so you can't find values of A and B, right, that would make that true. Well, now it's true when I threw the slash in here. Now it's always true, right, because they don't have the same number of components. But yeah, so pretty simple, right? Kind of like when matrices are equal, right? Pretty simple concept. Alright, so yeah, they're having you do that here, for some activities. I'll just leave these to you. These are pretty simple. Are these two vectors equal when s is 8 and t is 3? Do the components have the same values? Are these vectors equal when a is negative 3 and b is 0? Now, are these vectors... Now, right away, you can tell these aren't going to be equal ever because this has 3 components and this has 4 components. Right, so pretty easy. And again, another pretty easy one. There's only 3 of them. I'll just do this first one real quick. 2 vectors with 2 components, when are they going to be equal? When x plus 2 is equal to 4, so when x is 2. And when negative 4 is y plus 1, so when y is negative 3, these vectors will be equivalent. Right? And then you got another level where it's pretty similar, just with vectors with 3 components. And the last one here, yeah. Now, this one's basically a system of equations. Right? You have x plus y needs to be equal to negative 4, and 5x plus y needs to be equal to 12. And then you're solving that system. Right? But still, you should be able to find a value of x and y that would make these two vectors equivalent. Okay. All right, now the properties I was talking about. All right, remember, there's a set of objects called vectors. There are scalars, right, real numbers. And then there are 2 operations, scalar multiplication and vector addition. Now, here, when we're talking about Euclidean vector spaces, these Rn's, r to the nth, these sets of vectors with n components that are real numbers, we've already seen one way to define scalar multiplication and one way to define vector addition, and that's this way, right? These ways right here. So we've seen these already, right? Where u is some vector with n components in Rn, say v is another vector with n components in Rn, and little k here is a scalar, right? It's just in the real numbers, right? So the real numbers here, this is the set of scalars. This is not Rn, right? Notice they don't have the same like exponent or whatever. So as mentioned in previous sections, right, scalar multiplication is defined this way. If I take a vector and multiply it by a scalar, that's just multiplying each component of that vector by that scalar. And vector addition we've seen defined this way, right? If I add two vectors, vector addition, you just add the corresponding components, right? u1 plus v1, u2 plus v2, and so on. So vectors under addition and scalar multiplication have properties similar to those of real numbers. Some of these properties involve an identity element. Right? The identity element of a set with respect to an operation is an element that returns the input unchanged. Right? So for scalar multiplication, the identity element for the scalars is the number 1. Right? If I multiply a vector by 1, it doesn't change that vector. And then for vector addition, the identity element would be the 0 vector. Right? The 0 vector is a vector where all the components are 0. Right? If I take a vector and add the 0 vector, that first vector is unchanged. So they'd call the 0 vector the identity element. Right, hopefully that makes sense. The scalar identity is the number 1, as I mentioned. Right? You multiply a vector by 1, that vector is unchanged. The additive identity, right? The additive identity is that 0 vector. Right? You take a vector, add the 0 vector, the vector is unchanged. All right, then you have additive inverses. The additive inverse is just opposite, really. The way vector addition is defined here is just the opposite of all the components. The additive inverse of an element u is an element v such that u plus v is the 0 vector. So basically, like I said, the opposite of u, negative 1 times u, would be the additive inverse of u, because u plus the opposite of u gives you the 0 vector, gives you that identity element. All right, so the additive inverse of a vector is the vector you add to it to get the additive identity, to get the 0 vector in this case. And in the future, this will change. Right? What the additive identity is and what the additive inverse is will change depending on how scalar multiplication and vector addition are defined. But the way they're defined right now, the way they are defined here, this is, the 0 vector is the additive identity, and then the opposite, right, negative 1 times a vector is the additive inverse. All right. Then the first two properties involve the notion of set closure under an operation. So a set is closed if performing an operation between two elements of the set gives another element that is also in that set. So an operation that is closed over a set is also called a binary operation. For example, addition of two real numbers is a binary operation because when you add two real numbers, you get another real number, right? You don't get something else. So the real numbers is closed under addition, under that example. On the other hand, in contrast, subtracting positive integers does not always give you a positive integer, right? 5 minus 7 is negative 2. So the positive integers is not closed under subtraction, right? So the operation of subtraction is not a binary operation for positive integers. Because when you subtract two positive integers, you don't always end up with another positive integer. Okay. So, what are these properties that I've been mentioning so often? So, properties of Euclidean vector spaces, these, r to the nth spaces. These sets of vectors with n components and real number components, right? All right, so in order for a set of vectors with these operations of scalar multiplication and vector addition, in order for a set of vectors to be considered a vector space, all 10 of these properties must be true. All 10 of these must hold. If any one of these fails, your set of vectors is not a vector space. All right, so suppose u, v, and w are vectors, with n components and real number components, right? They're vectors from an n-dimensional Euclidean vector space, right? And suppose little a and little b are just scalars, right? They're real numbers here, just scalars. So again, the following 10 properties must hold if we're in a vector space, right, with scalar multiplication and vector addition. All right, so the first property here is, first off, the set must be closed under vector addition. That means if you take two vectors in the space and add them together, you get another vector in that space, not somewhere else. You must also be closed under scalar multiplication, meaning if I take a vector from the space and multiply it by any scalar, I get another vector from that same space, not some other space, not somewhere else. All right, then you have a bunch of addition properties. Must be commutative under addition, meaning if you add two vectors in either order, u plus v and v plus u, you get the same result. You have associativity under addition. So if you add three vectors, take any three vectors from the space, add them together, it won't matter which two you add first. You'll get the same result. You could add v and w first and then add u, or you could add u and v first and then add w. You get the same result all the time. There must be an additive identity. All right, that was mentioned up here. Right? There must be an additive identity element. So there must be a vector in the space such that, when you add it to a vector, that vector remains unchanged. And for our Euclidean spaces, that will be the zero vector. All right, for our Euclidean spaces with vector addition defined this way, that will be the zero vector. So the zero vector must be in the space, which it is. Every element must have an additive inverse, a unique additive inverse. So that means if you take a vector u, right, you take any vector u, all vectors, take any vector from the space, there's going to be another vector. Maybe the same thing, right? Like if it's a zero vector, right? the additive inverse of the zero vector would be the zero vector. But there's another vector, right, noted as the opposite of u, that's also in the space, that when you add them together, you get the identity element. You get that zero vector back. So every element, every vector has an additive inverse. All right, and then the remainder of these have to do with, scalar multiplication. Well, two of them have to do with scalar multiplication, and then the last two are distributive properties that involve both scalar multiplication and vector addition. So number 7, it's associative under scalar multiplication. So that means if you take a vector from the space, multiply it by two scalars, any two real numbers, it won't matter how you do it. You can multiply the vector by one scalar and then by the next one, or you can multiply the scalars first and then multiply it by the vector. You get the same result, no matter what. All right, for any vector in the space and any two scalars. There is a scalar identity. Right? Again, that was mentioned up here. A scalar identity. That means that there's some scalar that when you multiply a vector by that scalar, the vector remains unchanged. So here, for our Euclidean spaces and the way that scalar multiplication is defined, that's the number 1. Right. Then you have two distributive properties that need to hold. Scalars can distribute over vector addition or under vector addition. So if you take a scalar times a vector sum, you can multiply that scalar by each vector and add them, and you get the same result. All right, this is for any pair of vectors and any scalar. And switching the operations also works. You can distribute vectors under or over scalar addition. So if you have a sum of two scalars multiplied by a vector, you can distribute that vector and get the same result, right, for any vector and any two scalars. Right, so like I said, all 10 of these properties need to hold, need to be true for your vectors and your scalars, and the way scalar multiplication is defined, the way vector addition is defined, in order for your set of vectors to be considered a vector space. We'll see these properties again in chapter 6 as well. These are not going away. All 10 need to hold. I can't say that enough. Now they go through a proof here of one of them. A couple properties actually. So the proof of the first property, the closure under vector addition. Again, they're using our definitions of scalar multiplication and vector addition up here. So if U is some vector from Rn, right, n components that are real numbers, and V is some vector from Rn, and you look at their sum, well, if you add them the way that addition is defined, you're getting this vector here. And every single one of these, since U1 and V1 and U2 and V2 and UN and Vn, those are all real numbers there. Remember, adding real numbers makes another real number. So U1 plus V1, U2 plus V2, UN plus Vn, those are all real numbers as well. So this new vector, this sum, is also in Rn. So adding two vectors gives you another vector in Rn. It's closed then under vector addition. Same thing for scalar multiplication. If you take a real number scalar, multiply it by vector u here, well, you're just multiplying every component by another real number. That gives you just more real numbers, right? You multiply a real number by a real number, you get another real number. So multiplying a vector by a scalar gives you another vector in the same space. So it's closed under scalar multiplication. You can add vectors in either order, get the same result, because, adding two real numbers, you switch them, you get the same result every single time. So vector addition is commutative. And they leave the other 10, 4 through 10 here to you in some of the exercise. Oh, here's a property, one of the distributive properties, property 9, right? When you distribute a scalar over vector addition. So you just have to fill in the steps for the proof of that one, showing that a scalar A times the sum of two vectors u and v gives you the exact same result as A times u plus A times v, right? Distributing the scalar over the vector sum. So they start off for you, they just define the definition of vector addition here. U plus v is going to be this vector u1 plus v1, u2 plus v2, un plus vn, right? And then they multiply each of these by a scalar, right? Every single component is multiplied by a. That's the definition of scalar multiplication. And then what happened from step 2 to step 3 here? Right, well, the distributive property for real numbers was used, right? If you take a real number, multiply it by a sum of two real numbers, you can distribute. So to get this next line, we use the distributive property of real numbers. All right, so you have to know certain things about real numbers as well. Then from the third line to the fourth line, they just reused the definition of vector addition again, but went backwards. Right? If you have a1 plus a times u1 plus a times v1 for the first component, and a times un plus a times vn for the nth component, you can break this up into the sum of two vectors with a1u1 to a1un, or aun, and then av1 to avn. You can break it up, and that's just using the definition of vector addition again, right? But just going backwards. Come on. There we go. Put that there. And then finally, how did they go from this line to this line? Well, this is just the definition of scalar multiplication, but again, just going backwards. And there they have shown that a times u plus v would be a times u plus a times v. All right, that's proving the ninth property. Now the other ones, right, the other ones are actually in your exercises. I don't think I assigned them, but here's exercise. I would recommend doing them still, or at least looking at the proofs. Here's the associative property of addition, proving that. Proving that there is an identity element, an additive identity, right? That zero vector. Proving that the zero vector is unique, right? There's not another one. There aren't two different identity elements. Proving additive inverses are unique, right? Showing that for every vector, there's another vector that when you add them, you get the identity element, right? You get the zero vector back. This is that associative property for scalar multiplication, proving that. This is proving that 1 is the identity element for the scalar identity. And then this last one's property 10, right? That the other distributive property where I distribute a vector over scalar addition, right? A vector over the sum of scalars to get the same result. So you can take a look at those if you want. All right, proving the other properties, right? The remaining properties. Okay. All right. So next, we have subspaces of Rn, subspaces of Euclidean vector spaces. So these are just subsets. All right. So you can almost think of these as smaller spaces, but they're still vector spaces though, meaning all 10 of these properties will still hold for these smaller spaces. So when I add two vectors from these smaller spaces, I get another vector from that little space. When I multiply a vector by a scalar in this smaller space, I'll get another vector from the smaller space, right? So and so on. All 10 properties will still hold. So okay. So subspaces of Rn. So a subspace W of Rn is a subset of Rn, right? So that means it still has elements of Rn, right? So every vector in W will still have, n components of real numbers. But it's a subset of Rn that also forms a vector space, right? Meaning that all 10 of those properties still hold. Thus, if a set is a subset of Rn and satisfies the properties of a vector space, then W is a subspace. So some very, very basic, trivial examples of subspaces are the space itself, right? Because remember, a subset of a set contains elements from that larger set. Well, every set is a subset of itself. So Rn itself is a subset of itself, a subspace. And the set with just the zero vector, the set with just the zero vector in it, would also be a subspace of Rn, right? First of all, it's a subset, right? Because the zero vector is in Rn. And it would satisfy all 10 properties. Right? You take the zero vector, add it to itself, you get the zero vector again. So it's closed under addition. Take the zero vector, multiply it by any scalar. You get the zero vector again. So it's closed under scalar multiplication. And again, add the zero vector to itself in either order, same result. Add 3 of the zero vectors, because the only vector in that space is the zero vector. Add the zero vector to itself 3 times. It doesn't matter what order you do it in, what pair you add first, you're going to get the zero vector. The zero vector plus the zero vector would be the zero vector, so the zero vector is in there. It's the additive identity. The opposite of the zero vector is in there, right? The opposite of the zero vector would be the zero vector, so that's also in the set. So every vector in there has an additive inverse. Take any 2 scalars, multiply by the zero vector, it doesn't matter. You're going to get the zero vector back, so either of these will be the same. 1 times the zero vector is the zero vector, so 1 is the scalar identity. And any scalar times the sum of 2 zero vectors is going to be the zero vector, just like the right side. And any sum of scalars times the zero vector is going to be the zero vector, so these will be the same. All 10 properties hold for just the set with the zero vector in it. So that's a subspace of Rn. Now these are considered the trivial subspaces. Right, the set with just the zero vector, the set with just the additive identity, and the set itself, the whole space itself. But of course, there are subspaces that are between these. All right, and we're going to try to look at some of those. So a subset W of Rn that satisfies the vector space axioms, right, all 10 of them, is also a subspace of Rn, as I mentioned. However, not all properties need to be checked. A useful criterion for determining whether a subset of Rn is a subspace is given below. So, if W is a subset of Rn, that means all the vectors in W are vectors in Rn, meaning that properties 3 through 10 will automatically hold. Properties 3 through 10 will automatically hold. They're kind of inherited by the larger set. Right? If every vector in W is also a vector in Rn, then every single, all of the vectors in W will satisfy these properties 3 through 10, because they're vectors in Rn. The only 2 you don't know right away, the only 2 you gotta figure out, you gotta check, are the closure properties. And also, is there actually a vector in W, right? So that's what this is stating. So how can I tell if a set W is a subspace of Rn? So here's a theorem, right? Let W be a subset of Rn. Then W is a subspace, right? It's a vector space itself. It satisfies all 10 properties if and only if the following 3 hold. 1, the zero vector is in W. Now, I've seen other books, and you might see videos of mine later, because I made some other videos in a previous semester that I'm going to be sharing with you. This condition, that the zero vector is in W, you could also just say that W is not empty. If you just show that W has any vector, that's equivalent to this first one, right, along with the other 2 properties here. So just show that W has a vector in it. Show that W is closed under addition, right? So if I take 2 vectors from W and add them, I get another vector that's also in W. And that W is closed under scalar multiplication. So if I take a vector in W, multiply it by any scalar, right, say a real number a, I'm going to get another vector in W. So it's non-empty, closed under addition, closed under scalar multiplication. If you have those three things, and you know that W is a subset of a larger vector space, right? The vectors in W are vectors from a larger vector space. If you know that and these three things, then W itself will also be a vector space, will also satisfy all 10 of those properties. But you only need to check 2 of them, the closures. The other 3, the other properties 3 through 10, are inherited from the larger vector space. All right, so I'm going to go over a couple examples of this, maybe 3. We'll see how long it takes. Well, here, perfect. 3 examples. So determining if a subset of R, now this is for R2, all these vectors here are going to have 2 components of real numbers. Determining if a subset of R2 forms a subspace of R2. Right? So determine whether each subset of R2 forms a subspace. So I'm going to go to a piece of paper and we'll work with each one of these separately. Set W, set U, and set V. Okay, so the first one is this set called W. All right. Now W, they're saying, is a set of vectors, right? Vectors with 2 components, such that the second component is 3 times the first component. So W is a subset of R2. Right, and that's what this symbol means. This kind of sideways U with a half equal sign under it. This means is a subset of, not a subspace, right? Is a subset of. And all that means is that every vector in W is a vector in R2, which they're telling us, right? Every vector in here, if it has any vectors, we'll figure that out in a second. But every vector in here has 2 components with real numbers in it. Now the question is W a subspace of R2? Right, or is W also a vector space? Right, would it satisfy all 10 of those properties? Now you could go through and do all 10 properties. You could check them all for vectors in this set W. But like I said, there's no need to do that. Because these vectors are vectors from R2, properties 3 through 10 will automatically hold. Properties 3 through 10 will hold. Because we know R2 is a vector space. All right? So any vectors from R2 will satisfy, that commutative property through the distributive properties that I've shown you. The only ones we don't know hold are the closure properties. All right, so we need to go through now. First of all, before we get to those closure properties, we have to figure out, does this set even have any vectors in it? Because if this is empty, if this set has no vectors, what's the point? How could it possibly be a subspace? So the first question I'm going to answer is W non-empty? Does W have any vectors in it? Now their question is the 0 vector in W? Still, is there a vector in W? Well, the answer is yes. I can think of several. This vector. Well, first of all, yeah, the 0 vector would belong to W, right? Since, the second component is 3 times the first component, right? Any vector where the second component is 3 times the first component is going to be in this set. So yes, there is a vector in here. All right, this set is non-empty. Now some other examples. I mean, you could throw some more out here. You know, the vector 1, 3 is in W, right? Since you know, the second component is 3 times the first component. Right? And there's lots of other ones, right? This actually has infinitely many vectors in it, right? So it's definitely non-empty, and also has the 0 vector in it, so that's good. So now we check, you know, okay, properties 3 through 10 will hold because all these vectors are from R2, but what about the first two properties? All right, what about those closure properties? Those are the only ones that aren't going to be inherited from the larger set R2. So now the second thing I need to check, the second question I need to answer, is W closed under vector addition? And this is going to be the typical vector addition, the way vector addition is defined normally. All right. Like I said, we'll see later in like chapter 6, we'll see vector addition be defined in some other way for some other set of vectors. But the question now is W closed under vector addition? So how do we test this? Well, you take two vectors, two general vectors, generic vectors, don't use specific numbers. So suppose, you know, vector U equals, you know, say U1 with components U1 and U2. And another vector, say vector V, equals with components, say V1 and V2. Suppose that these belong to W. Right, so I'm taking two generic vectors from W. Now this would mean the following, right? This means, you know, since these belong to W, this means that for each of these vectors, the second component must be equal to 3 times the first component. So U2 must be equal to 3 times U1. And this other vector I said was in W must also satisfy the same condition. The second component V2 must be equal to 3 times the first component V1. Okay, now we're going to look at, all right, the question is W closed under vector addition? So that's the same thing as asking, is U plus V, these two, the sum of these two vectors, is this also in W? Same question. So let's take a look. Let's look at U plus V. Oops. All right. Well, if I use the way vector addition is defined, U plus V, you know, would have a first component of U1 plus V1 and a second component of U2 plus V2. Now, is this going to be in W? Well, the only way it's going to be in W is to answer this question, right? Again, this is the same kind of question. This will answer the same thing. Is the second component of this sum, is U2 plus V2 equal to 3 times the first component, 3 times the quantity U1 plus V1? So I'm going to answer, so this question and this question and this question are all answering the same thing. Well, yeah. What did we say earlier, right? Isn't U2 just 3 times U1? So this is the same thing as U1 plus V1 for the first component. And we said earlier, you know, hey, U was in W, so U2 must be equal to 3 times U1. And same thing for V2, right? V was in W, so V2 must be 3 times V1. And hey, isn't that just this, right? You can factor the 3 out. So the answer is yes. Yes, 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 yes. This particular set of vectors is closed under vector addition. Take any two of them, add them together, and you'll get another one that's also in W. All right, so we got property 1 holding. of those 10 properties, right? And again, 3 through 10 will automatically hold because these are vectors from R2. Now we just need to check property 2. All right, so the third condition I'm checking here is that second property of those 10 vector space properties. Now the question is W closed under scalar multiplication? All right. So again, let's just take vector u here. So let me just put this question up here, move it off the screen. All right. So let's just take vector u. Right? Again, I'm taking some vector from W, say vector u with components u1 and u2. And if it's in W, that means that u2 must be 3 times u1. Now also suppose that we have any scalar. Right? So suppose, I don't know, the little a here, suppose this is a real number, right? This is a scalar. Now the question is, right, so asking this question, is W closed under scalar multiplication, is the same as asking this question. Is any scalar A times any vector in WU, is this also a vector in W? Does this also belong to W? Well, let's see. Let's take a look at the scalar times vector U. Now, the way scalar multiplication is defined, and again, the way it's defined here, may not be the same way it's defined in the future. We'll see other definitions of scalar multiplication for other sets of vectors. But for right now, the way scalar multiplication is defined, A times U is going to be A times U1 for the first component and A times U2 for the second component. Now the big question is, again, is this vector also in W? So that's the same as asking this. If this is going to be in W, is the second component, A times U2, equal to 3 times the first component? So I'm going to answer this question. Well, yes. Remember what we said earlier, right? U was in W, so U2 must be 3 times U1, so I'll make that replacement. So this is the same thing as A times U1, and then U2 is 3 times U1. And isn't this equivalent to that, right? A times 3 times U1 would be the same as 3 times A times U1, right? These are all just real numbers. You can move them in any order you wish. So yeah, looks like it. Yes, W is also closed under scalar multiplication. So we've got property 1 closed under vector addition, property 2 closed under scalar multiplication, and properties 3 through 10, because all these vectors in W are from a larger vector space R2. And it's not, and it also has some vectors in it, has the 0 vector, has other vectors, is non-empty. So after all that, yes, W, that set of vectors, is a subspace of R2. I'll just say is a subspace. All right, it is a vector space as well. Right? And you might consider it like a smaller vector space than R2 because it doesn't have all the vectors from R2 in it, just the ones where the second component is 3 times the first component. All right. So I know it's a lot, right? Now this one took a while because I talked everything out. I wrote down every single question I was thinking. But these are the 3 things you're going to be checking when when you have a set, a set of vectors that's a subset of a larger set of vectors. Something you already know is a vector space. Well, then properties 3 through 10 will hold, and you just need to check if properties 1 and 2 hold. You need to just check those closure properties. Also, the set better have some vectors in it. All right, it can't be empty. All right, so let me look at another one. All right, so I'll write up the second one in that example and do the same kind of thing. Okay, so same question. I've got this set now called U. It has, vectors with two components that are real numbers in it. So U here is a subset of R2, right? A larger thing that we know R2 is a vector space, a Euclidean vector space, two-dimensional. So again, because of this, that's crappy. All right. Because of this, we know that properties 3 through 10 hold. 3 through 10. The only ones we don't know are 1 and 2, the closure properties. All right, and then the question again is, is U, yeah, it's a subset of R2. It's got vectors with two components in it, great, but is this set also a vector space? Properties 3 through 10 will hold, sure, but will all 10 properties hold for these vectors? So is U a subspace? Right, is it also a vector space? Do all 10 of those properties hold? Right, so the first thing I need to check, is U non-empty? Does it have any vectors in it? Right. Now, most notably, we'll check for, like they have in the book, in the ZyBooks, we'll check for the zero vector. Is the zero vector in this set called U? Well, let's look at the condition here. Every vector in this set has satisfies this condition. The product of their two components is 0. So remember what that means. That means either the first component or the second component or both are 0. So, 0, 0 does belong here. Right? The zero vector is in U, right? Since the product of their components is 0, right? It satisfies the condition. So that's good, right? It's not empty. It's got some vectors in it. In fact, it would have infinitely many. Here's another one. 1, 0 belongs to U, right? Since the product of their components is 0. 0, 2. This belongs to U as well, since the product of their components is also 0. So basically, any vector where at least one of the components is 0 belongs to U. So it's definitely non-empty. All right. Next question. All right, now that I know it's got some vectors in it, and it would satisfy 3 through 10, will these vectors in set U satisfy the closure properties? So the first question after that is, or this, after the non-empty question is U closed under vector addition? Right? The way vector addition is defined for a Euclidean vector space, the standard definition that we've seen. Okay. Well, right away, I'm seeing the answer is no. But let me go through a more general way, just using these two vectors. If I add those two vectors, using the standard definition of vector addition, the sum of these two vectors that I'm pointing to would be the vector 1, 2. And 1, 2 does not belong to U, because 1 times 2 is not 0. Right. So I'll get to that example. That's a counter example. But let's say I didn't see that. All right, suppose I didn't see that. So let's take two vectors from U. So suppose I have a little u, which has components, say again u1 and u2. And another vector called v with components v1 and v2. Say these are vectors in set U there. All right. And then we're going to add them up and see if the vector would belong to U as well, right? Is the sum of these two vectors also in U? Now, since they're in U, all right, since they are in U, then the product of their components, u1 times u2 must be 0. That's what it means to be a vector here in set U. So u1 times u2 must be 0, and v1 times v2 must also be 0. All right, so now the big question is u plus v also in set U? Because if it is, then yes, it's closed under vector addition. If we can find an example where it's not, again, you just need to find one example, one pair of vectors whose sum is not in U to show that that's not closed under vector addition. So let's do this. All right, so let's look at u plus v. That would be, under the standard definition, that would be u1 plus v1 for the first component, u2 plus v2 for the second component. Now, is this going to be in set U? So another question, right? So is the product of their components, u1 plus v1 multiplied by u2 plus v2, is that equal to 0? Because if that's equal to 0 all the time, then yes, the sum is, going to be in U. It'll be closed under addition. Oh, if I FOIL here, this is u1 times u2 plus, u1 times v2 plus, u2 times v1 plus v1 times v2. All right. Well, from earlier, we know that, the product of the u's is 0, the product of the v's is 0, so this is 0, and this is 0, but this stuff in here is not necessarily 0. What if u1 and v2 and u2 and v1, if u1 and v2 aren't 0, then we have a non-zero term here. So this is not necessarily 0. And then you got to show me a counterexample, right? So you just need to find one example where this does not end up being 0. So like my examples earlier, this vector belongs to U, and this vector, 0, 2, belongs to U, but their sum, which would be the vector 1, 2, does not belong to U, since 1 times 2 is not 0. So if you can find just one example of a pair of vectors whose sum is not in the set, then it's not closed under vector addition. So therefore, U is not closed under vector addition. So that first property, property 1, or was that property 2? One of the closure properties, right, does not hold. Yeah, 3 through 10 would hold, but not property, not 1 or 2, right? Well, property 2 would hold. The closure, it is closed under scalar multiplication, right? Because if one of these is 0, right, one of these would have to be 0 for this to be true. If I multiply by any scalar, you're still going to have a 0 in there. So it is closed under scalar multiplication, but as we've seen here, it is not closed under vector addition. So this set of vectors does not satisfy all 10 vector space properties. So therefore, set U there is not a subspace of R2. Okay? It would not satisfy all 10 vector space properties. All right. Now finally, I'm going to do this one last example, and then I'll read you some other ones. But what I'm doing here for these is what you're going to be doing for any of the exercises where you're asked, is this set of vectors a subspace of some larger set of vectors, right? Some larger vector space. All right, so this is the third example. Now again, this set V is a subset of R2. All right, it has vectors with two components that are real numbers. All right. Maybe, right? We have to check if it's out. But if it does, this would be a subset of R2. So the properties 3 through 10 would hold. So again, the big question is now, do the first two properties hold, the closure properties? All right, so first of all, though, is V non-empty? Now, if you combine this question with the closure under addition and scalar multiplication, you could also just ask, is the zero vector in here? Now, every vector in V is a vector whose second component is 3 more than the first component. So 0, 0 would not belong to V. Since, the second component is not the first component plus 3. So right away, I can tell you this set of vectors does not satisfy all 10 properties. It wouldn't be closed under vector addition or even scalar multiplication for that matter. But if that additive identity, the zero vector, is not in the set, it's not going to be a subspace. Okay, but there are some vectors in here, right? There are some vectors in here. Let's 3 0 0 3, that vector's in here, right? 1 4, right? Any vector where the second component is 3 more than the first component. So I mean, it's not empty, right? It is not empty. Sure, this again, we're seeing here, because the zero vector is not in there, we're going to see that this is not a subspace, doesn't satisfy, but it's not empty. All right, is it closed under addition? Is it closed under vector addition? All right, well, again, I only brought up 2 examples here, so let's look at this. I'll show you the answer is no. Watch, take the sum. These 2 vectors are in V. If I add them up using the standard definition, 0 plus 1, first component's 1, 3 plus 4, second component's 7. The vector 1, 7 doesn't belong to V. This is not in V, since the second component, 7, is not the first component plus 3. So, no. Same deal, it's not even closed under scalar multiplication. All right, let me show you that as well. I mean, we could have stopped after this. I could have stopped after this and told you this wasn't a subspace. But, let's go to the third one. Is it closed under scalar multiplication? No. I'll show you why as well. Take the vector 1, 4, and then a scalar. How about 3? 3 is a scalar. Right? If I take 3 times 1, 4, it gives me the vector 3, 12. Right, using the standard definition, the way that we've defined scalar multiplication. So I've taken a vector in V and some scalar, multiplied them, and look, I don't get a vector in V again. So again, you only need to show me one example where it doesn't happen to show that it's not closed. To show that something is closed, right, you need to show for all, right, in general. But to show that some set is not closed under a certain operation, you just need one example. And this is not in V, right, since the second component is not the first component plus 3. Right, 12 is not equal to 6. So definitely V is not a subspace, right? The vectors in V would not satisfy all 10 properties of a vector space. All right, so this is what you're doing for the rest of this. All right, now you read through that there. All right, so again, same thing. Now this is a these are all vectors where the first component is just -3 times the second component, right? Just replace x1 with some numbers here. The first component is -3 times the second component. Would this set of vectors satisfy all 10 properties, be a subspace? So again, you're just checking, is the 0 vector in there? Yeah. If I add two vectors like this, will I get another vector like this, where the first component's -3 times the second component? Yeah. And if I take any vector like this and multiply it by any scalar, say a, will that vector also be like this, where the first component is -3 times the second component? Yeah. So I'll tell you right now, this is a subspace of R2. And this one here. So let's read through the second one. This is all the vectors with two components, where the first component's not negative, and the second component's also not negative. So yeah, the 0, 0's in here, fine. 1, 5 is in here, 5, 10, pi square root of 3, whatever. Right, as long as the first and second component are not negative. Is it closed under addition? Yeah. If you take a vector with two non-negative components, add it to another vector with two non-negative components, you're going to get a vector with two non-negative components. So you'll get another vector in W, sure. But, is it closed under scalar multiplication? That answer is no. Because remember, that has to be for any scalar, any real number. So if you take a vector with non-negative components, say 1, 6, and multiply it by a negative scalar, say I multiply by -2, the vector 1, 6 by the scalar -2, you end up with the vector -2, -12. You end up with a vector with negative components, and that is not in W. So this isn't closed under scalar multiplication, wouldn't satisfy all 10 vector space properties, not a subspace. All right, and then here we have some vectors from R3. Again, you're checking the same stuff. All right. Would this set of vectors with 3 components satisfy all 10 properties? Again, you're only checking, they are vectors from R3, so you got properties 3 through 10. You just need to check, hey, is the 0 vector in there? Is it non-empty? And is it closed under addition? Closed under scalar multiplication. Same thing for this. All right, I'll do one of these. Challenge activity. So yeah, I'll do this first one. All right, same deal. Here we have a subset of R2, right? Vectors with 2 components. Now this set W has vectors from R2 such that the product of the components is not negative. So that means both of them are not negative or both of them are not positive. So like, 0, 0 would be in here. 1, 1, 2, 5, 10, 13. But also, -1, -1, right? Because the product of -1 and -1 is greater than or equal to 0. So 2 negative numbers, 2 positive numbers, or, one of them is at least one of them 0. But what you can't have is a positive and a negative, right? Set W doesn't have the vector 2, -3, for instance. 2 times -3 would be -6. That's not satisfying the condition. But it's got the 0 vector. It's got the 0 vector. If you add any 2 vectors from this, would you get another vector from this? Well, no. No. For instance, the vector -1, -3. -1, -3 is in this. And so is 1, 1. -1, -3 is in it. 1, 1 is in it. Add those. Well, no, let's go 2, 1. Sorry. So -1, -3 is in it. 2, 1 is in it. Now if I take -1, -3 and add 2, 1, I'd get 1, -2. 1 for x1, 1 for the first component, -2 for the second. That does not belong to W. So it is not closed under vector addition. Now, would it be closed under scalar multiplication? Yeah. If I take two positives, multiply by a scalar, they're still going to have the same sign, right? If you multiply by a positive, they'll still be positives. If you multiply by a negative, they'll both be negative and still be in here. Multiply by 0, you get 0, 0, which is in here. You take two negative components, the same thing. So like this is closed under scalar multiplication, just not vector addition. So it's not a subspace, so I'm not clicking that one. All right, so you just go through and figure out which properties hold. And 2 and 3 should be the same kind of deal where you're looking at, you're looking at another. Now this is just a vector with n components. A vector with n components. So you got to think just in general. And it's only the vectors such that the sum of all the components is 0. So would the 0 vector be in this? Yes, right? Because all zeros added up would be 0. Is it closed under vector addition? Is it closed under scalar multiplication? I leave that to you. And then after that, would it be a... Now, the last one's going to be checked only if the first three are, right? And then you have, your additional exercises. So again, like I said, for 513, I don't think I assigned 513. I would still recommend looking at 513 to see the proofs of a lot of those other properties, right? Properties 1 through 10 for the vector, those 10 vector space properties are of the utmost importance for you. You need to remember those. You need to know those for the rest of the course. They do not go away. The concept of a vector space is going to be paramount for the rest of the chapters. All right, so some of these are assigned, some of these aren't. Again, I would still recommend you look at all of them, and you got solutions you can look at if you want to check your work. Please try to work on the problem first, right? Try to figure out on your own first before looking at the solutions, right? You're not going to learn anything if you just copy the solutions down. And yeah, so hopefully this video helps guide you through this section 5.1 here. And of course, if you have any questions, please let me know. And thank you very much for watching.